Okay, all right. We'll get started now. Are there any questions from yesterday or no? Okay, we were looking at solutions to linear equations yesterday. Now we look at and we know that there are three types of solutions: either unique, no, or infinitely many solutions. We'll now look at cases, the different types of equations where this scenario occurs, and we'll also look at the corresponding geometry. And when we are dealing with geometry of linear equations, we'll only do the column view. We won't go back to the traditional row view anymore. Okay? Right. And the column view is, for example, if you have a problem like this, where a x equals b, then the essential geometric question you're asking, well, I have a vector b, I have two vectors a1 and a2, which are the columns of a. How much do I scale a1 and a2 and add them together so that I get to b? Right? And here the particular solution is, well, here there is only one way you can scale a1 and a2 and obtain b. That is essentially you take 3 times of a1 minus 2 times of a2, add them together and you get this. And if you substitute 3 for x1 and minus 2 for x2, you'll get, is that correct? Well, maybe we'll verify. Minus 2 for x2, you will get this. Actually, correct? Okay, let's try and solve this. So we take 3 times a1, that's 3 plus minus 4 minus 2. Yeah, that's correct. Yeah, we get minus 1 plus 1. Okay. Right. So in this particular case, it turned out that we had a unique solution. Okay. Then we could ask, well, what is the general condition for us to have unique solution when you have Ax equals b? I will simply state the conditions for now, and then later on we'll see geometrically also that it makes sense. When you have Ax equals b, you will have a unique solution when these conditions are satisfied. When a square, okay, when the columns a1 and a2, or in general all the columns of a, if you make a set out of the columns of a, then that set is linearly independent. That's the second condition. Third condition is b should be in the span of the set of columns of a. What does it mean? Okay, let me ask you this. What does linear independence mean? What is the definition, and what is our intuitive understanding of linear independence? Yeah, go ahead. You should know this by now. Set is what? Okay. Is dependent, okay. Great. Okay, let's go a little deeper. Fine, I agree. So what is not dependent? Don't tell me if it's independent, it's not dependent. Right, okay. I see that you remember some parts of it. Remembering is the first step, but you have to remember the whole thing. You cannot simply say all the alphas are equal to 0. I don't know what that means. Yeah. I'm giving you a chance to recall. Being able to recall is an important thing. If you're not able to recall, that means I'm helping you identify that you don't know something that you should know. That means it's a chance for you to go back and revise it. Okay, all right. Linear independence is a property associated with, and that's why I gave that one sheet. You have to look at that. Is a property associated with the set of vectors a1 to, let's say, am, such that if you take a linear combination of these vectors, and you want to produce a zero vector, if the only way you can produce a zero vector is if you set all the alphas to 0, then you say the set is linearly independent. If there is any non-zero combination for the alphas that will produce a zero vector, then it's a linearly dependent set. Okay. So for you to have a unique solution for Ax equals B, the set of the columns of A have to be linearly independent. Okay. What is a span? Linear independence is the property of a set. What is a span? Is it a property? Is it a set? Is it a vector? Is it what is it? Great. Okay. What did you say? Okay. So if you have a set of vectors A1, Am, the span is also a set. Set contains things, and the things that the span contains are all the possible linear combinations of these vectors. Right. So this states that you're trying to solve Ax equals B. If B is in the span of the columns of A, then there is a unique solution. It's a third condition. Right? And when these conditions are satisfied, then Ax equals B is always solvable and will give you a unique solution. Okay, so that's essentially the condition. Now let's look at the okay. Now let's go back to this. Right? Well, this has a unique solution, yes, we just saw, and the geometry associated with it is this. A1 and A2 are two vectors in R2, and they are not collinear. That means they are linearly independent. Okay. The only way I can take the linear combination of A1 and A2 and reach the origin is if I scale both A1 A2 to 0. Okay. B. So if you have two vectors, so R2 has dimension 2. That means, what does it mean when I say the dimension of, what is the dimension of a subspace? How do you know the dimension? Yeah. In what? Hey, hold on. What is A? I'm asking you a general question. If I have a vector space, how do I find the dimension of the vector space? You don't know, look at the sheet. It's the number of elements in the basis of in a basis for that vector space, right? What is the property of a basis? If I say a set is a basis for a vector space, what does it mean? A span. Okay. So in the case of R2, R2 has dimension 2 because you can generate all vectors in R2 using a set of two vectors such that that set is linearly, if that set is linearly independent and has two vectors, you can generate any vector in R2, right? Here you have a condition of two vectors A1 and A2, which form a linearly independent set. That means you should be able to generate any vector in R2, which means any vector you choose in R2 must be in the span of A1, the set A1, A2. Right? So you have a linearly independent set, and you have B, which is in the span of A1 and A2. So that's why this particular system of equations has a unique solution. We'll now look at a situation where you could either have a unique solution or no solution at all. Okay? For example, what about the first equation? Does that have a unique solution? Does it have a solution where B1 is minus 1, 1? No, it does not. There is no x1 you can choose that will satisfy both 2x1 equals minus 1 and x1 equals 1. Okay. So this does not have a solution. What about the second one? Okay. Second one does have a solution. Okay. And if you look at the geometry, right, now A has only one column, right? And it's still in R2 because remember in the column view, we are always looking at Rn. Rn is the number of what? Number of rows in the matrix A, or the space from which the columns of A come from. Right. Okay, this is R2. There is only one column. That's what I've drawn in blue. In the first example, B1, this is B1. Second example, this is B2. The first example was not solvable, whereas the second example was solvable. And maybe it's geometrically clear why that is here, right? You have A1. When you do AX, right, the operation you're essentially doing is that you're taking the linear combination of the columns of A. There is only one column. So if you take if you do linear combination operations and with one vector, what operation are you doing? You're simply scaling it. You're taking different scaled versions of the vector. If this is A1, the different linear combinations of A1 will simply lie on this line. So if your B1 lies on that line, then I can of course reach B1 using my A1 vector. If it does not lie on that line, then there is no way, there is nothing I can do in terms of AX, or there is no X I can choose that will give me that new that vector B1, right? That's why this has no solution. This has a unique solution, or it has a solution. Let's just put it that way. In this particular case, it has a unique solution. Okay, all right. So the situation of us having a unique solution or no solution will arise when our matrix is tall. Okay. The set of vectors that we have, the set of columns we have, form a linearly independent set. And whether that system of equation has a solution or not depends on whether your B lies in the span of the columns of A, or if it does not lie in the span of columns of A. If B belongs to the span of the columns of A, then we say this system of equation is solvable and it has a unique solution. If B does not belong to the span of the columns of A, then it has a solution. Okay? And that's essentially what this diagram depicts with the two examples. When B2 was in the span of the columns of A, so that had a unique solution. And the columns of A were linearly independent. That's why you have a unique solution. In the case of B1 is not in the span of the columns of A. In that case, you cannot solve it. Can you hear me? Hear me. Yeah, so now we've looked at when you can have a unique solution. We've looked at the case where you have no solution. We look at the third case, infinitely many solutions. Now we consider AX like this. Okay. In this case, A has three columns. Okay. The columns of A are still from R2. Okay. We want to be able to solve this. Okay. And if you remember from your from school, that when the number of unknowns is more than the number of equations, then you have infinitely many solutions. That's essentially the case here. Number of equations is 2, number of unknowns are 3. So you are likely to have infinitely many solutions. That is not always the case, but in general, if you have more unknowns than equations, then the possibility is that you have infinitely many solutions. Then you can have the possibility of infinitely many solutions. And the geometry associated is this. Now we don't just have two vectors in R2, but we have three vectors: A1, A2, and A3. So the columns of A now form a linearly independent set. You're right. Why? Two. Why? You're saying no. Why? Why do they not form a linearly independent set? Well, that's because you can represent A3 using A1 or A2, or you can represent A1 using A2 or A3, or you can represent A1 using A2 and A3, or A2 using A1 and A3. So this set is not linearly independent because one of these vectors can be represented as a linear combination of the other two. Okay, and the moment you can do that, that means you are not uh, uh, okay. Okay, okay, let's continue. Okay. And of course, uh, these three vectors, you can take linear combinations of those and generate any element in R2. Now, so some of the conditions for having infinitely many solutions is that you have a fat matrix. Whenever you have a fat matrix, you have the possibility of having infinitely many solutions. Okay. The moment you have a fat matrix, linear independence is out. Linear independence of the columns is out. You are for sure you will have the set of columns of A will be linearly dependent set. Okay? Okay? So to have infinitely many solutions, B should be in the span of the columns of A. And when you have these three conditions satisfied, well, if you have fat matrix and the columns are anyway linearly dependent, if you have this and this satisfied, then this system of equation is always solvable and you will always have infinitely many solutions. Okay? That's essentially saying, well, I could have produced B using just A1 and A2, right? So what I can do is I will produce, because I can produce B using A1 and A2, because I have a third vector now, I can, with A1 and A2, I'll produce some other vector, which is not A3. And then using this newly produced vector, I can use these two to produce B. That means I can now, and there are different vectors that can produce using A1 and A2, which are not A3, and still be able to solve for B. And that's essentially what gives you infinitely many possibilities to generate B from A1, A2, and A3. Right. So those are a set of conditions for the three possible solutions. Right. Now we'll try and uh, summarize all this and see if we can have a concise set of conditions that you can use for figuring out whether given set of linear equations have unique, no, or infinitely many solutions. Okay. Right? The three possible solutions that you can have essentially depends on two things. Well, it depends on A and B, right? Those are the things that determine your equations. So we now have to come up with conditions on A and B that will essentially allow us to know whether this given system of equation has a solution, what type of solution it has, right? Now let's first consider the case where A is full rank. Okay? Okay. And A is an n cross m matrix. If A is full rank, right? If it's n cross m, right, and the rank of A is n, okay, what can you say about the possible shape of that matrix? It's full rank, it's an n cross m matrix, and I say the rank is n. There are three possibilities: square, fat, or tall. Which of the three possibilities or which of the possibilities do we have? Sorry, fat. Okay, is that the only possibility? Square. So when you have full rank matrix where the rank is equal to the row rank n, then the matrix can only be fat or square. Okay, right. So whenever you have a fat or a square matrix and the rank is n, okay, you can always solve it. It doesn't matter what B is, you can always solve it as long as its rank is n. Okay? When n is equal to m, that means when it's square, then you have a unique solution. When n is less than m, n has to be less than m, right? Because rank is n, the rank is the lowest of the number of rows or columns. So n has to be, if when n is less than m, then you have infinitely many solutions. Okay? Here, whether you have unique or infinitely many solutions does not really depend on B, as long as the rank is, as long as it's a full rank matrix. Okay. On the other hand, if the rank was m, then what possibilities do we have for the matrix? What shapes? It's square, it can be square. Another possibility is tall, right? So when rank is equal to m, when the rank is equal to the column rank, then you have a tall or a square matrix. Whenever that happens, whenever you have a full rank tall or a square matrix, one possibility is out. You will not have infinitely many solutions. If you have a solution that's unique, or you don't have a solution, right? And that depends on, and there the condition depends on, can depend on B. Okay. If it's a square matrix and it's full rank, row rank equals column rank, it's essentially the first condition here, right? Then you have a unique solution. That's done. But if m is less than n, okay, then it depends. This is whether or not you have a unique solution or or no solution depends. Depends on B. If B is in the span of columns of A, then you have a unique solution. Okay. If B is not in the span, then you don't have any solution. And in fact, you can relate all of this and go back here. Go back to the three pictures that we have, that we've had. Okay. Full. Full column rank or row rank, always solvable, unique solution. Rank is equal to m. Okay. You either not square. You either have, when B is not in the span of the columns of A, no solution. When B is in the span of columns of A, unique solution. Here, next one. Rank is equal to n. 2, fat matrix, full rank, always solvable, and infinitely many solutions. Okay, that's when A is full rank. Okay, so now the question is, what if A is rank deficient? That means the rank of A is less than the minimum of the number of rows and columns. Okay, you can have that situation. For example, if you had a system of equations like this. What is the rank of this matrix? Well, the rank of a matrix is essentially the number of columns you can take to form a maximum number of columns you can take from the matrix so that you form a linearly independent set. Here the rank is 1, which is less than 2, right? Number of rows and columns. So this is a rank deficient matrix. When you have a rank deficient matrix, you cannot have a unique solution anymore. Okay? That's out. And there are only the other two possibilities. And that depends on B and its relationship to the columns of A. If B is in the span of the columns of A, then you have infinitely many solutions. If B is not in the span of the columns of A, then you have no solution. So that's essentially the complete set of conditions for knowing whether or not what kind of solution AX equals B has. It turns out that this is also too complicated. I put all this in just for us to smoothly transition to the most compact summary of conditions to know whether AX equals B has what kind of solution AX equals B has, and that's essentially this what is shown in this slide. For rank deficient matrix, yeah, okay. Let's give me an example of a rank deficient matrix that's not square. Or think of one. What about this? Is this rank deficient or not? Okay. Whenever you see this, right, see if you can represent any one of the columns as a linear combination of the other columns. The moment you see that, it's rank deficient. Here, I can represent the second column here as 2 times the first column, or I can represent the first column as half times the second column. The moment you can do that, you're done. They're linearly dependent. It's rank deficient. Well, again, that's not entirely correct. At least you have linearly dependent columns, and depending on the shape of the matrix, you can have a rank deficient matrix. Okay. This one is okay. Do the columns of A form a linearly independent set? No, they don't know. Second column is exactly the same as the first one. Third column is also exactly the same as the first one. That means the second column can be represented as 1 times the first column. So linearly dependent set. What is the rank of this matrix? Essentially, how many columns can you take from this matrix to form a set so that it's linearly independent? Turns out here it's only 1. Because I can represent everything else using just the first column. This has rank 1. Rank of A, there is 1, which is less than 2. So now you have a case where it's rank deficient. Same thing applies here. Is this full rank? No, the second column is 2 times the first column, so the columns do not form a linearly independent set. And what is the rank of this matrix? It's just 1, right? Which is less than 2. The maximum possible rank for this matrix was 2, and the actual rank is less than that, so that means this is rank deficient. So yeah, you can have rectangular or square rank deficient matrix. It depends on, it depends essentially on this. It depends on the dimension of span of that's essentially the rank of A. Again, if this confuses you, dimension of span of something should go back and revise. Okay. Right. These are essentially the conditions that we need to know whether Ax equals B has or what kind of solution Ax equals B has. Whenever B is not in the span of the columns of A, there is no solution. You cannot solve it. And which makes sense. The only thing I can produce by doing Ax is essentially the span of columns of A. Because span of columns of A contains all the linear combinations of the columns of A. When you do Ax, you're essentially taking the linear combination of columns of A. So if the right hand side B is not in the possible in all the possible vectors that you can generate using Ax, then you cannot generate B using Ax. That's essentially what this states. B not in the span of the columns of A, no solution. Let's say B is in the span of columns of A. Then it depends on that. Then whether you have unique solution or infinitely many solutions depends on essentially the rank of A. Okay. If the rank of A equals the column rank, okay, then you have a unique solution. If the rank of A is less than the number of columns you have, then you have infinitely many solutions. This is equivalent to saying, let's assume B is in the span of the columns of A. If the columns of A form a linearly independent set, there are m columns. When I say the rank of A is m, that means those m columns form a linearly independent set. If the columns of A form a linearly independent set, then you have a unique solution. It doesn't matter whether A is tall or square, okay? Or fat. And when the rank of A is less than m, which essentially means that the columns of A are not linearly independent, then you have infinitely many solutions. Okay? And you can relate all of these conditions again to the three examples that we saw earlier. And these are essentially a complete summary of the conditions on A and B for us to know what type of solution we have. Okay. I mean, of course, you should remember this for now, but over time you should be able to logically argue why this is the case. Okay. And you should be able to, at least if you've forgotten something, you should be able to then figure out, argue logically to arrive at these conditions. Okay. Right. So that's essentially about what are the conditions for the different type of solutions you have. Okay. Now we look at the solutions themselves. Okay. For whenever you can solve the problem. If you cannot solve the problem, there is no solution. There is nothing to discuss. But when you can solve the problem, you can either have a unique solution or infinitely many solutions. Okay. In general, the most general cases, there are infinitely many solutions. Unique solution is just a special case of that. Good. So the most general form of a solution to a linear system of equations like this can be written as the solution equals some xp plus xh. Okay, xp is called the particular solution, and xh is called the homogeneous solution. Okay, and the idea is pretty simple, and this is something that happens with linear equations. Okay, xh is essentially the solution to this equation. And that's essentially the definition of what is a homogeneous solution. Whenever you see, for a linear system, you see a homogeneous solution, it's essentially the solution of whatever you're trying to solve equated to zero. That's it. And this says, in general, you have any solution x for x equals b can be written as sum xp plus xh. And that makes sense because here, if I say X is a solution, right, to this, and I say the set, I mean, XH is it. There is another solution XH which is equal to 0, right? Now, if I take my X, if I add XH to it, it'll still be equal to B because uh, this matrix multiplication is distributive. So X B, this is equal to 0. That means I still get X equals B. So that means whenever you solve X equals B, right? If you take that solution, if you add any solution to that or any homogeneous solution to that, you'll still be able to solve Ax equals B because homogeneous solutions essentially go to 0 when you multiply it by A. And that brings us to case of when you have a unique solution or an infinitely many solution. When the set of all homogeneous solutions for solutions of A, that's this set. This essentially means the curly brackets mean it's a set XH. So this set contains elements XH such that A times XH will be equal to 0. This homogeneous set has all the solutions, and if you take any one solution from here and multiply it by A, you'll get 0. Okay. So you will have a unique solution to X equals B if the only possible homogeneous solution is this. There is no other XH you have or non-zero XH that you have such that A times XH equals 0. But whenever you have a situation where a non-zero XH when multiplied by A gives you 0, then you have a situation where you have infinitely many solutions. Right? Because if X only possible value for XH is 0, and let's say you solve X equals B, if you add the homogeneous solution, that is equal to X because the only possible value for the homogeneous solution is 0. But if XH was non-zero, let's say my solution was 1, 2, and solutions of this form, alpha minus alpha, let's say these are all homogeneous solutions, then any solution like this will also solve X equals B. Okay? And another interesting fact is this set of all homogeneous solutions of A is actually a special set. And it is in fact a subspace of Rm. You'll have to go back to think about what a subspace is. Remember what a subspace is. And because here, what space are the elements XH from? Are they from Rn or Rm? A is the n cross m matrix. Rm. So this the set of all homogeneous solutions will essentially be a subspace of Rm because these are all elements from Rm. Okay. Now we will look at geometry of different solutions or the solutions that we have for different types of equations that have unique solution or infinitely many solutions. Okay. Remember that if you have n cross m matrix, one interpretation of a matrix like this is that it's a linear transformation. Okay. Linear transformation that takes elements from Rm and produces, if you multiply any element from Rm by A, you'll get elements from Rn. Okay. Means if you have this space, Rn, matrix A will take a specific element from here and then produce another element here. Okay? So we can think of A as some a linear transformation. That's what I'm trying to say. Let's consider this example where A is this 2 cross 2 matrix. Okay? That means A takes elements. So this when you do this operation AX, A takes elements from R2, that is Rm. So in this case, Rm is R2, and produces elements in Rn, which is in this case R2. Right? So I can essentially draw both my input space and the output space like this. This is the input space. Output space. Right? And A essentially does this mapping. Okay. Now, if I take an element from here, essentially this point, that is an element from R2 or Rm, and if I do AX, right, it will produce this element. Okay. In fact, this element is 3 minus 2. That was the solution to this. Right? The element 3 minus 2 gets mapped to minus 1, 1. That is essentially what AX equals B means. If you take this element X, do the linear transformation using the matrix A, you produce B. So this point here gets mapped to this point. If I choose another point here, it might produce a point here. If I choose a point here, and because we know that this system of equation has a unique solution, every point here gets mapped to a unique point on the from the input space gets mapped to a unique point on in the output space. Okay? And that mapping is essentially given by your matrix A. Okay? And whenever you have a unique solution, right? The only value of X that will produce 0 by doing AX is means in this particular case, 0 gets mapped to 0 and nothing else gets mapped to 0. That is equivalent to saying the set of all homogeneous solutions is just this, just the 0 vector. There is no other element in the set of all homogeneous solutions. Let me ask you this, right? So in this particular case, I said 0 gets mapped to 0, and we know that this point gets mapped to this point. Okay. What will any point on the x1 axis get mapped to? Let's say I choose. So I choose this point. What do you think this will get mapped to? Can you say anything about that particular vector? The way I've drawn it here, it's along the x1 axis. So what will that vector look like? Second element will be 0. Right? So it has to be of the form. If it is of this form, can you tell me what this might get mapped to? Where this might get mapped to in the output space? Well, I've given you X. All you have to do is do AX and tell me. No, so this is X, right? If the X is of this form, what will I get if I do AX? Huh? No. What will you get if you do this? Alpha what? You didn't have to multiply it out. Column view. You're taking alpha times the first column, 0 times the second column. So it's alpha alpha. That means points along this axis, right? Where do they get mapped to? Here. They'll get mapped to points along here. So this line gets mapped to this line. And if I choose something here, that will get mapped to point along this line. Okay. Right. Now we look at another case. Where A is tall. Okay. What is Rm now? Yeah. What is Rm in this case? It's R1 and Rn is R2. I should not have drawn this. There is no x2 axis. Ignore that. It's only the real line. So this is just the real line. So this particular matrix, a tall 2 cross 1 matrix, takes elements from the real line and maps it to a two-dimensional space. Maps it to R2. Now, if you choose any element here, right? So in this particular case, if I choose this element, it'll then get mapped to only points along this line. Okay, that line is essentially the span of that single column that you have. So this point here will get mapped to this point. If you choose another point here, it'll get mapped here. So what you're seeing is here also there is a unique solution. The only thing that gets mapped to 0 is this. Right? Even though this matrix A maps elements from a real line from a one-dimensional space to a two-dimensional space, the actual points you can produce actually fall on a line. So you're essentially just mapping a line to a line, except that the line is embedded in a higher dimensional space. That's all. Okay? And here also you have a unique solution. Well, no, I should not say that. Here, as long as you choose a point along this line to solve for x, you will always have a unique solution because there is always a point on the real line corresponding to any point on this line. If you choose any point outside that line, then you cannot solve it anymore. Okay? So this is for a tall full rank case. Now look at the other way around. What if you had A which was fat, right? What is Rm here? Rm is R2 and Rn is R. So in this case, your input space is R2, space is just R. You can choose any point in the space, and that will essentially get mapped to a line here. But in this particular case, there are infinitely many solutions. If you go back to the condition, you'll see that this is actually full rank, but that means it's always solvable. But rank is the number of columns, number of rows. It's equal to the row rank. That means you have infinitely many solutions. Right? Now, if you choose any point, right? For example, let's say I choose this point. Okay? This point we'll see it gets mapped. Well, I've chosen this point, so this point gets mapped to here. And you could ask now, well, what about the homogeneous solutions? In the previous, in this case, again, the homogeneous solution was simply this. The only homogeneous solution here was 0. But that is not the case here anymore. Okay, I could ask you then, well, what are all the possible homogeneous solutions for this x equals 0, where A is 2, 1? What all possible values of the vector x can produce a 0 vector? 0 is always there. What about vectors of this form? Anything of this form will produce, right? And by choosing different values of alpha, you're producing all possible homogeneous solutions. Now, if you plot them in the input space, these are the different possible values of the input. They will essentially form this line, which passes through the origin. That's essentially a subspace. Okay? So this dotted green line that you see, that is essentially the homogeneous solution, set of all possible homogeneous solutions. But in general, we know that any solution is X particular plus X homogeneous. So if I choose a point, right? Let's say I choose this point, and that produces B, then that point plus all the homogeneous solutions should also produce this point B, right? That's essentially what is shown by this thick red line. That is essentially the set of all possible points in the input space that will produce this one vector B. Okay, and that's why I've written as xp plus xh. You can choose xp to be any point on this, and if you add this line to that point, then you get all these solutions. Okay. So here again we are saying, well, you're here in general, this matrix A is supposed to map from a two-dimensional space to a one-dimensional space. Okay. But what is happening here is, in fact, a whole bunch of lines get mapped to a single point on the output space. Okay. And if you choose any point along this line, right, you will always get the same B here when you do X. So this is X. But the moment you move out of this line, the B that you produce here will be different. Okay. So what I'm saying is, if in the input space, if you move parallel to this, parallel to the homogeneous solution, X will not change. If you move in any, even by a little amount in a direction perpendicular to the homogeneous solution, the value of X will change. So if I move either in this direction or in this direction, B will either move, as long as I move only in this direction, you will always produce the same B. B does not change. Now we'll look at, so all the previous cases that we've looked at, right, were all full rank matrices. This was a full rank square matrix, full rank tall matrix, and this is a full rank fat matrix. Now let's look at a rank deficient case. This is rank deficient. The maximum possible rank is 2. The number of linearly independent columns here is 1. The number of linearly independent rows is also 1. It's rank deficient, less than the maximum possible rank. Now I could ask, well, what can we say about the homogeneous solutions for this system? It's definitely not the zero vector alone anymore because it's rank deficient. What are all the possible? There are infinitely many solutions. I'm asking, what are all the different possible values of different possible vectors that will produce a zero vector such that let's write it down. 1, 2, minus 1, minus 2 into x1, x2. I want this to produce a zero vector. What possible values of x1 and x2 can I choose? 1, 1, 2, 2, 3, 3. Well, anything of this form. So all vectors of this form, essentially for different values of alpha, form the homogeneous solution for this system of equations, and that's essentially this line. This dotted line is the set of all homogeneous solutions, and the set of all homogeneous solutions form a subspace, so it has to pass through the origin. It's a straight line passing through the origin in R2. R2. Okay. Now, if you choose any point here, let's say I choose this point. This point will get mapped to some point here. Okay, and in fact, from that point, if I move in a direction parallel to the homogeneous solution, I will produce the same point here, B. Okay. If I move, of course, orthogonal direction, if I choose another, so this entire line will produce only this vector B. Now this entire line, which is parallel to this line or to the homogeneous solution, will probably produce another point here. And of course, this line produces a zero vector. Right? If I choose a line here, that will produce some point here. So when you have the rank deficient case, even though R2, your A is mapping from R2 to R2, because it's rank deficient, it's mapping entire lines to a specific point in your output space, right? And in fact, because it's rank deficient, it actually cannot reach any point in R2 in the output space. It can only reach actually a line. You cannot produce anything outside this line, right? Because A1 and A2 are linearly dependent. So you can see what A1 and A2 are. They lie on the same line. That means all you can produce is essentially what falls on that infinitely long line. So this happens when you have a rank deficient matrix. Okay? That you won't be able to reach all points in your output space. Right? So that means you can have situations where you have no solution because all the points in the output space cannot be reached. But if you have a full rank matrix, all the points can always be reached. You always have a solution. Whether you have infinitely many or unique depends then on what is your input space. If the input space has the same dimension as the output space and your full rank, then it's unique. That's the first example we saw, 2 cross 2. If you have a full rank matrix, but you have this condition, then you essentially have entire lines that get mapped to a single point. That means you have infinitely many solutions. Okay. Let's maybe do an example where you try and tell me the homogeneous solution and what gets mapped to something on the output space. Let's do this example. Well, I don't have to produce a B. That is my A. Now tell me what kind of mapping we will have. The first thing we do is we have our input space. Both are R2 because it's a 2 cross 2 matrix. We know that this point will get mapped to this point. That is always true for all linear transforms. 0 gets mapped to 0. Now we want to know this. What is the set of all possible homogeneous solutions for this particular case? Sorry, what is the first value? Okay. Okay, let's see. Two alpha. So that will give me 2 alpha minus 3 alpha. That'll give me minus alpha. That won't give me 0. Yeah. D alpha minus alpha. Yes, that's correct. So all points of this form will now produce the 0 vector. So what would that correspond to here? So if I were to ask you to plot this subspace, this is a subspace. Can you plot that subspace here? Let's say this is 1, 2, 3. Yeah. 3 minus 1. Okay. Well, it's a line. We've got 2 points, 0, 0, and this. So essentially the line would be this. That's your homogeneous solution. Will be here. Fine. Now, let's say I choose the point. What is this point? It's 2, 1. Okay. Now I ask, what does this point get mapped to? Where does this point get mapped to? Well, where does this line get mapped to? Let me ask you that first. This dash line. Well, it's a trivial question. It's a homogeneous subspace. Homogeneous subspace gets mapped to 0. So this always goes to 0 under the transformation A. Now I'm asking, where does this point get transformed to? 2, 1. This is 2, 1. Well, you don't have to worry so much. You simply multiply A, you compute AX. I've given you X. This is X. Five, 10. That's all. This will get mapped to, well, oh, bad. Okay. Let's do 1, 1. It's my plot. I mean, my region here is too small to plot 1, 1. Maybe that's simple. Does it? It's still big. Okay. So let's say this is 4. 8 is here. I'm going to say 8 is here. And that's what it gets mapped to. This gets mapped. This point gets mapped all the way to this point. Now I ask you, is that the only point that gets mapped to, what is this? What did you say this was? 4, 8. This was 1, 1. So 1, 1 got mapped to 4, 8. I'm asking you, is that the only point that gets mapped to 4, 8? Hey, hold on, no. No. You have a non-zero homogeneous solution. So if you take anything from the homogeneous, so if I take 0, add it to 1, 1, I'll still go to 4, 8. If I take any point here, add it to 1, 1, I will still go to 4, 8. Right? That is equivalent to saying, well, if I take this vector and I take this vector, right? If I add them together, that is essentially my, I'm going to call this my XP, my particular solution. Or particular solution is that one particular solution that gives you that gives you the B that you want. Okay, this is some homogeneous solution. If I add the two of them together, that point will also get mapped to 4, 8. Right? So that point will simply be what? So you do the parallelogram law of vectors. this point will also get mapped to 4, 8. Can you give me another point? Well, you choose another point in the homogeneous solution. I've chosen this vector. I'll choose this. Then that means I add this vector to my particular solution. It'll produce this. In fact, all possible points along this line all the points along this solid green line will get mapped to 4, 8. Okay. And to generate that, you needed two things: a particular solution and the homogeneous solution. Homogeneous solution we've already found, right? We chose some point that is a particular solution for 4, 8, and then if you add the homogeneous solution to that, you get everything else. Well, now you could ask, well, what if you had chosen, well, by chance I've chosen 1, 1, which produces 4, 8. What if I had chosen something else? What if I had chosen, let's say, this point as my particular solution? Doesn't matter. If I had chosen this point, for example, if let's say I had chosen this, right? This would be what? No, not 0, 1. Or let me choose this. Easier for me to do. What would this point be? This point gets mapped to 4, 8. So this has to be, right? Let's say I had chosen this as my particular solution. Now, if you take this point and you add anything from here, if you add these two, right, you'll still produce a point. So you'll still produce that line. It doesn't matter what point you choose as your particular solution. The moment you add your homogeneous solution, you'll essentially get that solid green line. Okay? I hope that clarifies how linear transformations work. This is all, I mean, we've chosen to display everything in R2 because you can visualize it easily on a sheet of paper. The ideas apply to R3 as well. So if you have a 3 cross 3 matrix, that's full rank, right? Then every point in this three-dimensional input space has a unique point in the three-dimensional output space, and they're mapped through A. If A and 0 is the only point gets mapped to 0 there, right? Now, if you have a rank deficient matrix, okay, the maximum possible rank for 3 cross 3 matrix is 3, right? Rank deficient could be 2, 1, or 0. Okay, if it's 2, right, what will happen is you can only produce a plane in your output space, a two-dimensional space in the output space. Okay? So what will happen is your homogeneous solution will essentially be a line. Okay, so if you choose any point in R3, and if you simply add the homogeneous solutions, so entire lines get mapped to a point in the plane. And if you move in three-dimensional space, if you move orthogonal to a line, that means you're moving in a plane, and essentially that plane gets mapped to your output plane, right? Let me ask you this: in the two-dimensional case, if you're rank deficient, right, the two possibilities are rank 1, rank 0. What kind of mapping does this do? If I have A that is like this, yes, so it essentially takes all of R2 and maps it to 1 point, 0. Okay. That brings us to an idea that confuses the hell out of people. Maybe the previous students are still confused, but yes, so we come to something that is just not easy to wrap your head around. Okay? This idea of 4 fundamental subspaces. Okay? So whenever you have a linear transformation from Rm to Rn, whatever we've looked at so far, the geometry that we've looked at so far of the different kinds of mappings that take place, have four subspaces associated with them, two in the input space and two in the output space. Okay. Input space is, remember, Rm, output space is Rn. I'll simply define them now, and then we'll look at what these mean. The four fundamental subspaces are the column space of A, the row space of A, null space of A, and null space of A transpose. Okay, or this is also sometimes called as the left null space. Column space of A is fairly easy to understand. Okay? And all of these are subspaces. Okay. That means they are sets which satisfy the property of being a vector space. The column space is a subspace of the output space, Rn. Okay, that's what I've written here. And column space is usually written as C of A, this calligraphic C of A. Whenever you see C of A, that means we are talking about the column space of A, which is a subspace. And it's nothing but the span of the columns of A. It essentially tells you what all can you produce if you do the operation AX, where you're free to choose X to be anything you want. And remember, X comes from Rm. That's essentially what I've written here. The column space of A is the set of all vectors of the form AX, and this vertical line simply says such that, okay, X belongs to Rm. That means X can be anything you want. You can choose any element from Rm, and if you multiply it by A, the matrix A, you produce a vector, you put that into this set. You choose another X, multiplied by A, you put that into this set. So all that you can possibly generate by doing X is the column space of A. Okay? Another way to say that, the column space of A is the span of the columns of A. Okay. If that is clear, the row space, or at least if the definition is clear, the row space is essentially the same thing. It is simply the set of all linear combinations of the rows of A. Okay, and that's why the reason it's written as C of A transpose is because if you do transpose operation, rows become columns. So it's equivalent to saying the column space of A transpose is essentially the row space, right? Because the rows became the columns, the row space is essentially then C A transpose. And again, the definition is set of all elements of the form A transpose Y. But notice here that Y comes from Rn because you've transposed it. A was Rn cross M. A transpose is M cross N. So if you take the linear combinations of rows of A, right? The rows of A are from Rn. Rm, sorry, see. The rows of A are from Rm. Yes. The rows of A are from Rm. Okay. So if you take the linear combination of the rows of A, you will produce vectors in Rm. That's why it's here. The row space is a subspace of Rm, the input space. Okay. You can simply write it like this as a linear combination of A transpose. Another way we could have written this without confusing people is you say, well, you take Y transpose A such that Y belongs to R. Multiplying a matrix by a row, you take the linear combinations of the rows of the matrix A. This is an equivalent definition of this. These two are equivalent. But in the way you understand it is linear combination of rows of A. Rows come from Rm, that means it has to be a subspace of Rm, the input space. Right? next one is this null space of A. We've already seen what this is. This is simply the set of all homogeneous solutions, and it's usually written as n, calligraphic n of A. And whenever you see that, that simply means if I give you a set and I say this is the null space of A, that means if I take any element from that set and multiply it by A, I'll get 0. That's all. This is set of all homogeneous solutions. Right? And what is this a subspace of? Rm or Rn? Well, it's homogeneous solution. It has to be the input space. So it is a subspace of Rm. Right? So the null space essentially refers to the input side of things. So it's Rm. The column space refers to what you can produce by doing Ax. That means the output. That's in Rn. The row space is the linear combination of rows of A. Rows is the number of columns. Number of columns is the size of the input space. So the row space is in the input space. Okay? And again, by symmetry, what is left? We have C of A, we have N of A, we have C of A transpose. So it's most likely that there is also a N of A transpose, and that is essentially what is called the left null space of A. Okay? The similar definition to A. So if N of A is a set of all X such that Ax equals 0, then N of A transpose is set of all Y such that A transpose Y equals 0. Okay? And because we've transposed it, okay, the left null space is in fact a subspace in Rn, the output space. Okay? It's often when the order of difficulty in grasping these things, column space is usually easy, null space is also easy, row space sounds a bit strange, left null space sounds the strangest thing. But we will come to what that is a little, after this, right? But again, like everything else we've seen so far, I would simply just remember this to start with. Maybe the column space is a null space, you have an intuitive feeling of what that is. Right? In fact, we've been talking about the column space and null space pretty much in all these visualizations. This is the null space, the dotted line. Okay? The column space here is, you can produce everything on the real line. That means the column space is the real line. In this particular case, this dotted line is the null space of A. This line, which we can produce by doing X, that's your column space. What about here? Where is the null space here in this particular example? What is the null space? Null space is simply the set of all homogeneous solutions. What is the set of all homogeneous solutions here? Oh no, hey, the input space is R1. It's just R. It's a thing. This is 0. Here the null space is simply this 0 element. What about the column space, which is in the output space? It's not all of R2. Because column space is what is it that I can produce by doing Ax, and all you can produce by doing Ax is this line. So that dashed blue line is your column space of A. What about here? Where is the null space? It's a 0. What about the column space? So the green line here, right? That is just that is just to say that this point gets mapped to this point. But the column space is what all can I reach in the output side? Well, because it's full rank, every point here gets mapped to a unique point here. In fact, the column space here is all of R2. So here you can reach every point in R2. That means the column space is all of R2. So one way to think about this is, we will again refine, this picture is not entirely correct, but maybe to start with this is okay. let's say this is Rm, this is Rn. Okay? A does this mapping. Okay? The column space is, let's say I divide, again, as I said, what I'm saying here is not entirely correct, but as a first step, I think this is a reasonable way to understand it. If you divide the output space like this, then the column space is essentially the part of the output space that can be reached by simply doing AX. If you are completely free to choose, if you choose any point from the input space, right, and you multiply that point by A, the part of Rn that you can reach by doing this operation is your column space. This is all we can reach. Okay, that's the column space. Now, we can divide, let's say we can divide this. And let's say there is a region here. Okay, and if you choose any point from here, okay, and let's say that point always gets mapped to 0. And that is your null space of A. That is the region of Rm, the input space. And if you choose any point from that space and you multiply by A, you will always get 0. That's the null space. And that leaves us with two other spaces, one in the input space and the output space. Those are the other two. In fact, I'm going to leave this as white. Okay. If the yellow colored region is the region of the input space, and if you choose any point from that that produces 0, C of A transpose, that's the row space. Okay. If you choose any point from the row space, that will essentially get mapped to a non-zero point in the output space. And in fact, since the column space is the only region that you can reach in the output space, so it has to end up in a point in the column space. Okay. See, and notice that the null space has 0. The row space also has 0. So, both of them have the 0 vector. Okay. Of course, if you take 0, it will produce 0. And because 0 belongs to both the row space and the and the null space, and it also belongs to the column space. So what I'm saying is still correct. 0 from the row space will get mapped to 0 from the column space. But if you take a non-zero value from the row space, it will, by definition, produce a non-zero value in the column space of A. Okay, that leaves us with one little space or one part of the output space that we've not talked about, right? That is essentially the part of the output space that you cannot reach using A. It's kind of forbidden. You can never reach there if you simply do X. Okay? And examples of that is here. Here. The column space is this line. Everything else is part of, again, not completely correct. Anything outside this line is part of the left null space. That is, those are points you cannot reach. Here, the null space has turned out to be only 0. But if you go here, right, the last example, this is actually good. This has all the spaces that we talked about. And all of them have all the spaces. It's just that when they're full rank, two of those spaces are just zeros. here. This is the null space, the dotted line. This entire line gets mapped to 0. Okay? And I said, if you go to a point, and if you move parallel to the null space, right, or the homogeneous solution, all points will produce the same point here. If I'm at this point, let's say I produce B. If I move parallel to the homogeneous solution or the null space, I'll still produce B. That's essentially what I meant by saying this entire line produces the B vector. And what can be produced by AX is the column space, and that means this dashed line that you see, that's the column space of A. This is the null space of A. Okay. And if you remember, I said, well, if you move parallel to the homogeneous solution, AX does not change. But if I move perpendicular to the homogeneous solution, then AX does change. You get a new value for AX. So what that will mean, as we'll see later in the next module, a subspace that is orthogonal to the null space. I've not defined what it means for two subspaces to be orthogonal, but for now, just in this case, to a line that is orthogonal to the homogeneous solution line, that is in fact your row space. In fact, if you move along your row space, you will actually move along your column space. If I move along the null space, you don't move along the column space. You just stay at that point. Okay? So if I'm here, right, I'm at B. If I move in this direction, this point does not move. But the moment I start moving in this direction, this point will start moving back and forth here. Okay? That means, so we have the null space, row space, column space. You probably can already guess where the left null space is. Left null space is perpendicular to the column space, which essentially means by doing AX, you can never move in a direction perpendicular to the column space. That means that direction is forbidden. Okay? It's not that the entire region is forbidden, it's just that direction is forbidden, which essentially keeps you then in that line, in the column space line. Okay? All right. That's all I wanted to say for now. Please go and revise this. Again, the first time you come across this is confusing as hell. At least the row space and the left null space, but over time, kind of you get used to it. Okay, that's all. Thank you. See you guys Monday.